One of the major problems a Hyperloop faces is its very own aerodynamics. Shockwaves form on it, and that, among other nuances, makes simulating its aerodynamics problematic to say the least. In this episode, we'll look at the latest research solving this aerodynamic problem, which is, in large part, why we're not already zipping around in underground high-speed tubes. And we have a special guest to share his latest research on solving this problem with us. We're joined by Benedikt Geiben, who is a PhD student researching how to more accurately simulate hyperloops at sonic speeds. He's at FH Aachen in collaboration with RMIT, and the method he's researching is something called HTLES. Welcome, Benedikt.
Thank you very much. Thank you for having me.
Thanks for being here. So a while ago when we were talking, Benedikt actually remarked to me how it's incredible that he's even researching aerodynamics, considering that he didn't do very well in high school to begin with, and didn't even know that aerodynamics was a thing until well into his undergrad, and that he only started aerospace engineering because he got inspired by a video game, which who among us can say otherwise?
Yeah, absolutely.
So that video game, I think you told me, was Kerbal Space Program.
Yes, Kerbal Space Program. I have no idea how long it has been since I've played that game, but I gotta be honest, it's a little bit embarrassing, but that game made me study aerospace engineering. Especially the space part was what I was interested in most. But as you've already said, I kind of only got into what I'm doing right now well into my undergrad studies, and here I am.
Yeah, well, the Kerbal Space Program, there's still some people on YouTube posting videos about the game, so it has a loyal following.
Yeah, I believe so. I think it's still an active community. It's a great game. If you are at least somewhat interested in like space dynamics and orbits, I think it's wonderful to play around with. So absolutely have a look if you're interested in that.
Yeah, okay. So to begin with, can you explain to us what a Hyperloop is?
Yes, absolutely. Very simply said, it's some sort of vessel, often called a pod, basically a kind of streamlined capsule that is being shot through a near vacuum tube. The more generic term, which was used before SpaceX even used the term Hyperloop, is evacuated tube train. And I think that explains it already quite well what it is. And to be honest, before we get started, I just want to say that I think it's pretty obvious that the term Hyperloop and the concept is somewhat loaded. I think it's a very controversial topic, let's say, and
Okay.
I get a lot of the controversy around it. But I just want to say, whether you think it's a good idea or not, whether you think it's purely hype or not, the research that surrounds it and the research that has been spawned by the topic, that is what is interesting and fascinating at the moment. And I think this is what we want to talk about. So independent of what you think about Hyperloop, I think the research topics surrounding it are very, very interesting.
Well, one example would be, back on the space idea, using rockets in low-density atmospheres is a similar kind of application then.
Yeah, absolutely. I think the kind of fluid dynamics that occur are at least similar, right? We do have compressible flows, we might have shock waves, we have low pressure environments, so that does lead to similar Mach numbers, Reynolds numbers, very comparable.
Yeah. So what kind of aerodynamic phenomena exist on Hyperloops that we know of so far?
I mean, there are multiple ones, right? We have a boundary layer forming around the vessel, around the pod. That means we have at some point a laminar turbulent transition. We have blunt body separation. Depending on the operating conditions, we might even get shock waves around the pod. And especially that kind of shockwave stuff. So the operating conditions where we get those shocks around the pod is where my research is mostly focused right now.
Okay. So you said blunt body separation. Can you explain what that is a bit more?
Yeah, so a blunt body, I mean, I think that's kind of obvious, right? We have streamlined bodies. that is something that you can imagine quite easily. And a blunt body is practically the opposite of that. So if a body is not really streamlined, not designed to curve the streamlines nicely around it, then we have this blunt or bluff body. And in a blunt or bluff body, it's very common that the boundary layer just at the end of the body just can't follow the contour of the geometry anymore. And that leads to a separation. And flow separation or boundary layer separation in general is always connected to a lot of drag increases and possibly to spectral behavior. That means we might get some fluctuations, maybe some excitation of the structurals of the structure. And all of that is connected to it being a blunt body.
Okay. So you said that increases the drag. So it's not just the pressure drag that would increase naturally, but also in this case, would it increase the wave drag component?
Yeah, absolutely. So I think that is something which not every aerodynamicist might agree with me, but from my point of view, we only have two general drag types, right? We have pressure drag and we have friction or shear drag. The shear drag part is the actual friction of the air of the boundary layer with the pod itself. That is at least somewhat easy to explain and capture. And then all other forms of drag are just parts of pressure drag. And when we have a separation, a blunt body separation, independent of the Mach number, independent of any high-speed effects, we do get a lot of pressure drag. When we now accelerate to a point where the flow around the pod is going nearly supersonic or getting to a sonic state, then we get something which you've already mentioned, like wave drag. And wave drag is additional pressure drag due to the shock wave, occurrence of shock waves. And that kind of adds up to all the other forms of drag which are already present even without any shock waves.
Yeah, I understand. I think you're right with the shear compared to pressure definition, because there are so many different topics in aerodynamic subtopics and they all have the different definitions. For example, in aeronautical, there's profile drag, which incorporates skin friction and pressure drag together, and then induced drag is something different and the wave drag is something different. So it just depends on the general field of how they try to define it, but the general overarching ideas are shear and pressure drags.
Yeah, absolutely.
Yeah. So that means that the Hyperloop's shape affects its aerodynamics. How would a blunt rear or front compared to like a more high-speed Japanese Shinkansen kind of pointed front and rear differ in terms of their aerodynamics?
Well, now that's exactly what depends on the operating conditions. So I think before we can actually answer that question, we need to talk a little bit about the operating conditions that define the state of such a Hyperloop pod. So the key things are, when we actually look at the physics that surrounds a Hyperloop pod, is the air that flows around the pod and through the tube itself. And that means we have two things that are kind of the key component, the key parameters. On one hand, we have the actual velocity of the air, right? So if the pod is going very fast, obviously that has an impact on its operating conditions. Slow, fast, okay.
Yep.
On the other hand, we also have the so-called blockage ratio. So that means how much of the cross-sectional area of the tube is actually blocked by the pod itself. And that part is quantified by the so-called blockage ratio. And both the speed, quantified by the Mach number, and this blockage ratio define the overall operating conditions. And depending on these operating conditions, the shape of the pod has significant or basically not a significant influence on the overall drag. So if we compare, when we go into how these conditions are made up, right? We've talked about the speed defined by the Mach number and about the blockage ratio defined by how large the pod actually is within the tube. And if we are around this limit, this limiting line between the blue shaded and the red shaded region, we are at the isentropic limit. And if we are below the isentropic limit, that means we have no shocks, we have no local supersonic flow, we are simply in the subsonic region. And in the subsonic region, the front shape and especially the rear shape can have significant influence on the overall drag, because drag is mostly driven by the separation and by the blunt body separation.
Yep.
Once we go above those conditions, so if we go, for example, at a blockage ratio of 0.4, we go from Mach number 0.2 to Mach number 0.7, we are crossing the boundary into the above the isentropic limit. Then we get something called choked flow, and that means we get shock waves, and those shock waves, as you've already mentioned, create wave drag, and this wave drag immensely increases the overall drag and kind of overshadows all other drag components. And from that point onwards, the actual shape of the rear and even the front of the pod don't matter that much. I mean, they do matter, don't get me wrong. There's a lot of optimization possible and happening. But just the occurrence of shock waves increases drag so much that everything else is kind of irrelevant. And that is important to keep in mind when we talk about and think about how to actually shape a Hyperloop pod.
Yep. So you said that the wave drag component overshadows everything else. What kind of factor are we talking about? Like a 5-to-1 factor or 10-to-1 factor?
That depends on what kind of Mach number exactly we are talking about, especially what kind of shock strength we have. So shock strength is usually measured by the Mach number just in front of the shock wave, so the local shock wave. Yep. In practice, it's kind of unlimited. So, for example, in larger parameter studies done in the late 2010s, we've seen that, for example, the drag coefficient, which is a normalized quantity to normalize the drag to any operating conditions, the drag the drag coefficient can go from like somewhat normal numbers like 0.1, maybe 1, can go up to 10, 100, 150, because once you're pushing towards higher and higher Mach numbers and higher blockage ratios, you can basically increase it to values which are outside of any normal reach. So the actual shock strength and the operating conditions, you are kind of limitless in where you want to push.
Yeah. And just back on this graph where you said isentropic compared to not, so by that you mean if it's isentropic, it's reversible, compared to when a shock forms, then it's no longer reversible.
Right. That's exactly it. So the isentropic limit marks is kind of the border between the region where all flow remains isentropic. Obviously, isentropic only in the sense of compressibility. We do still have a boundary layer. We do still have shear flows, etc. So it's not reversible in its full thermodynamical sense, but we don't have a shock wave. We don't have this non-isentropic shock wave effect. So this is exactly the boundary between no shock wave and shock wave occurrence, and that is what we call a choked flow. Choked flow boundary.
Yeah. Okay. So up until now, what has been the method or methods used to investigate the aerodynamics of hyperloops?
So in practical terms, we kind of have two main things we can do, right? And until now, the focus has been on CFD and RANS-based CFD in particular. And that is for good reason, to be honest. The question is, why do we do CFD, so numerical work, over experimental work? So I kind of think about it this way. When we imagine wind tunnel in general, be it in CFD or in wind tunnel work, we always do something called a coordinate transformation, right? So
Okay. Yep.
we don't really let an airplane fly through the air. We actually
Yep.
keep the airplane stationary and let the air flow around the airplane.
Yep.
And that works quite well, right? I put my airplane in my wind tunnel, my airplane is stationary, I let my turbine or whatever spin up and let airflow flow around the airplane. Works. Now, when we talk about the Hyperloop, we get some special things we have to keep in mind. Because what happens when we do the same thing for a Hyperloop pod? Well, let's do the same coordinate transformation. In practice, we just learned everything that moves before is now stationary and the other way around. That means our Hyperloop pod, stationary, that makes sense. Our air now needs to move around the Hyperloop pod, that also makes sense. But then we also have the outer tube, right? The actual tube the Hyperloop pod is inside of.
Yep.
And that tube in the real world is stationary.
Yep.
That means in our wind tunnel experiment, what we would have to do is to actually move our walls around the Hyperloop pod. So we would need to have a moving wall boundary at the outer limits.
Yep.
And that is something we can capture quite easily in CFD, but that is something that is extremely difficult to do in an experimental setup. That can be done, right? If you look, for example, at car aerodynamics, cars also have a moving road, and there are wind tunnels, high-speed wind tunnels, even Formula One aerodynamics, where they do have a moving road, but it is difficult to do. So the focus
that's also a
for
different
now,
scale.
Yeah, exactly.
Yeah.
The focus for now has been on CFD mostly.
Yeah. So you talked about the moving wall boundary condition, or the more accurately, I guess, the difference in the speeds or velocities on the Hyperloop compared to the wall surrounding it. How do you have that factored into CFD? Do you use simply a slip wall condition or a moving wall condition?
So what we would always do is use a actual moving wall boundary condition.
Yes.
And that moving wall boundary condition is set to the same speed as the inlet air. So that means in the beginning, when the air is accelerated, or when the air is coming in from the inlet, there is actually no shear layer between the wall and the flow because they are moving at the exact same speed. And once they get close to the actual pod, this is what you can see in this image right here, right? The air is accelerated, the flow tubes are getting pinched, and right here, the wall is still moving with the same inlet velocity, let's say maybe 100 meters per second, but the air has to accelerate around the pod, meaning it's now maybe 150 meters per second. In this case, it would be going like 300 meters per second because we do get a shock wave. And then we do have a shear layer between the outer wall and the flow, and we do get a boundary layer, and that boundary layer does have a significant impact on the overall simulation. So if you want to do this in CFD, or if you want to do it experimentally, you kind of need to have a moving wall boundary, or at least try to break it down into smaller specific issues which you can tackle without the moving wall boundary. But at the overall system level, the moving wall boundary does have a significant influence on the overall flow.
Yeah, okay. So we talked about earlier, and I researched a bit earlier, that sometimes scale models are used for Hyperloops. Can you talk a little bit about that?
Yes. So we just talked a little bit about why experimental or wind tunnel experiments are difficult. I gotta say, there is experimental work going on. I think there's a team in South Korea, if I'm not mistaken, and they actually just built a small tube with a pod, and everything scaled down a little bit. And so that does actually work. And in that case, if you're moving your pod, you do not need a specific moving wall boundary. Your wall just stays stationary. But you've correctly pointed out, in that case, we have scaled models, right? And Scaled models in CFD or in fluid dynamics in general have an important influence, or need to be kept in mind, because when we scale something, it changes the overall scale of all other fluid elements.
Yep.
And to kind of keep it similar, we have something called the Reynolds number. I think that's probably something most of your viewers will be familiar with. And the Reynolds number gives you the possibility or the ability to compare different cases and get similar, or theoretically even exactly the same result, as long as your Reynolds number stays the same. In this case, when we talk about compressible flow, we have another number we have to keep in mind, and that is a Mach number. So when we do scale models are absolutely fine as long as both the Reynolds number and the Mach number are kept the same, and the scaling has been a accurate geometric scaling, right? So if you change the geometry, that's not really working. But if you scale the geometry, if you have the same Reynolds number, the same Mach number, then a scale model is perfectly valid to do research with, be it at an experimental or numerical level.
Okay, so the question I have is, with scaling, it's always difficult. For example, going from aerodynamics to hydrodynamics, you're often forced to choose to scale some things accurately, but other things not. With the Reynolds number versus the Mach number, if you were to keep the Mach number the same, then and increase or keep the Reynolds number the same, or vice versa, wouldn't that create a mismatch between one or the other non-dimensional terms?
Yeah, that it's you're laying your finger perfectly into the wound of all transonic researchers, because that is difficult, right? If you only have to scale the Reynolds number, it's easy. You can scale velocity, you can scale viscosity, so just use a different fluid, for example. But if you have to scale both, then you have an issue, because they are interconnected, right? For example, velocity is both in the Reynolds number and in the Mach number. And that means you kind of have to wiggle that around. And the only real thing that I'm familiar with to solve this is to actually get different gases instead of air. So for example, in Cologne, there is the European Transonic Wind Tunnel, and they do operate with air, but they operate at super cold conditions. So they have much, much cooler airflow. But at cooler conditions, so if the air is only maybe 100, 150 Kelvin, you do get very different viscosity levels. And that gives you the ability to both scale the Reynolds number and the Mach number somewhat independently, because you're now controlling the viscosity, which is only part of the Mach number. Of the Reynolds number, sorry. And you are at the same time controlling the temperature, which is also part of the Mach number due to the speed of sound. And so that is a very difficult problem to solve, but it has been done, and I think many transonic wind tunnel facilities around the world do it very similarly. We have to somewhat change the actual gases, the actual fluids we are working with, be it a totally different gas. For example, you could do pure nitrogen instead of air, or you could do something completely different, or just do it at cryogenic temperatures.
So to talk about the equations, the speed of sound is a square root of gamma RT, whereas the Reynolds number is density times velocity times the length scale divided by the viscosity. So you want to find terms that don't appear in both, isolate them and change them to be able to change that particular characteristic number without affecting the other one.
Yes, exactly.
Okay, so moving on to the method that you're using to simulate the Hyperloop. You mentioned RANS. Is there a reason why RANS is used predominantly?
Yes, and it's a very simple reason. It's cheap. The main thing when we talk about CFD is that we have a lot of computational effort, basically. And that computational effort can be put into two things. You can either increase your methodology, basically, your cost for the methodology. For example, you may have heard about large eddy simulations or even direct numerical simulations, LES, DNS, which have a very, very high computational cost, which resolve a lot of the turbulent scales, which means they represent the reality of physics much closer, but you have to put a lot of computational effort into that. The other way you could put your computational resources is to put into more parameter studies or into more geometric detail. And for example, when we look at, I'm from Germany, so the automotive industry has a big impact here. And whenever I talk to someone from the automotive CFD side, they always tell me, well, 20 years ago, we thought LES was just around the corner. And our next computer, we will do LES. Our next cluster, we'll do LES. And every time they did that, someone else from the company said, well, we could do LES, or we just now model our front grille, our cooling system, our wing mirrors, whatever, more accurately. And they always chose to go into that route. They always chose to make their geometric model, their overall physics model, like including cooling, including more complex coupling, etc. They always chose that route, and they always got good enough results and had a much better picture of the actual geometry instead of going into that LES route and putting more resources into an actually higher order method.
Yeah. Me personally, I'm with LES because I worked in this exact field. I think 2090 or so was when people were kind of estimating LES would be around for computers to be able to do it. And then 2100 or so was DNS. And whether that's accurate or not, who knows? But LES is almost becoming the holy grail, and it's becoming more used, but still it's definitely the DDES family is what's being used, which actually brings us to your method. So you are using something called HTLES instead of RANS. Is that right?
Yes. So HTLES, which stands for Hybrid Temporal LES, and this is a method developed over the last basically 10-15 years, but over the last 5 to 10 years there was big developments, I think from French researchers mostly, who pushed that into an usable model, and that model is implemented into Star CCM, which I use mostly for my research, and hence I use HTLES as for my research, for my applied research.
Okay, so can you describe what HTLES is and how that is different to RANS and DES?
Yes. So HTLES, the key thing is already in the name, right? We have the hybrid temporal large eddy simulation. And I think it makes more sense to start at the back, actually. What is a large eddy simulation? So we already talked a little bit about that. LES, kind of the holy grail right now of CFD. And LES is already a step-down method, right? At the very end, we have direct numerical simulation. In theory, we resolve all spatial and temporal scales. That means every little thing that is happening in the flow, be it at a micrometer scale, is resolved by our simulation. Whether it has a big influence on the overall result doesn't matter. We resolve everything. And that obviously works, right? If I model a system perfectly, then it's not longer a model even. It's an actual clone of the physics. However, we've already talked about that. That is so extremely expensive. We practically can only do it for academic work in super small cases with long compute times. It's done on a fundamental research level, but not on an applied level. And the next step would be the large eddy simulation. And large eddy means we capture most of the spectrum, most of the temporal and most of the spatial spectrum, but we don't capture everything. So a lot of the tiny, tiny turbulence influences, which are happening on a micrometer level, on a microsecond scale, don't have that much of a influence on the actual bigger, larger scales, which we humans in a meters and seconds range actually care about.
Yep.
And so the first thing to understand is how do we get from this DNS to LES? And there are two general approaches. You can do an implicit LES or an explicit LES. And implicit and explicit don't refer to the discretization in this case, right? You might know implicit discretization from your CFD classes or your fluid dynamics classes, but in this case we are talking about how we actually cut out the part of the DNS which doesn't interest us. And the main idea that has been established in the last 20-30 years is that we can simply use 80% of the total turbulent kinetic energy as a rough approximate for the entire flow. So as long as we capture these most important, these upper 80%, then the lower 20% which remain have such a little influence that it doesn't really matter. And if we do that implicitly, and that is the only form that really matters for this case today, if we do that implicitly, that means we are simply using equations which could resolve it more, which could resolve it temporally and spatially more, but we are simply letting something out, right? We are simply not resolving it well enough. Instead of doing a mesh which has, 10 million cells, we simply use a mesh with 5 million cells, and that means the smallest scales are simply not resolved. And thereby we are implicitly filtering out, that is an important term, we are implicitly filtering out these smallest scales. And that is how we get from the DNS to the LES.
Yep. And the assumption being that the smaller scale stuff is not as important. Therefore, you can ignore it and still get pretty good accuracy, or in compared to what we can do currently, very good accuracy.
Exactly. It's not like we can just say that. It's not a proven statement. But the established consensus
Assumption.
has been into that direction, that we can capture a lot of the interesting scale stuff for us humans when we just resolve the larger ones. Obviously, it has an impact, but the impact can remain very small depending on the case.
Yep.
Now we have this general LES, right? We have this filtering step, which removes some part of the actual spectrum, some part of the turbulent kinetic energy, so some part of the smallest scales are not resolved anymore. Now let's go to the hybrid temporal part, because this is the interesting stuff that actually makes the HTLES model special and relevant to this case. The filtering we just talked about is a spatial filtering only. That means the only thing I'm changing is I'm just making the cells physically larger. That means I cannot resolve features, turbulent features, which are smaller than the physical cell size. In practice, that is obviously that can be implemented, but in practice that means I'm only dependent on the spatial resolution. The hybrid temporal part of HTLES now adds also a temporal filter. And this temporal filter means we are not only checking for the spatial resolution matching our results, but we are also looking for the temporal resolution matching our actually intended resolution and intended LES results. And this is kind of the special sauce of HTLES, that it does implement this two-prong approach, right? We have the temporal part and the already established spatial part.
Yep.
And together, these now form the hybrid temporal LES model. And if you want, we can actually take a look at the equation supporting this, because
Sure.
I think it's actually less difficult than it seemed at the beginning.
Okay.
So
definitely.
So if we look at equations 12 and 13, right?
And this is from your paper, by the way. If you're listening to this and you want to see this paper and these equations, just look at the link below in the description, and I'll link it to Benedikt's paper here.
Yes. So before we look at these equations, let's have a look how a turbulent spectrum typically looks like, right?
Yep.
So in figure 9, we have a turbulent kinetic energy spectrum. That means, what do we see? On the lower axis, on the x-axis, we see the frequency in this case. This might already be, this may also be represented as omega, for example. Yep. But in this case, it's the actual frequency f. And on the left-hand side, we have the power spectral density of the velocity fluctuation, which leads to a quantity which is in square meters per second squared, which, if you do the calculation, is actually just joule per kilogram. So we have a specific energy integrated over the frequency, which leads to the area under the graph actually representing the total turbulent kinetic energy in the simulation.
Okay.
And you can already see with increasing cell counts, so going from blue over green, red, orange, we see that the spectrum is getting bigger and bigger and bigger, meaning we are resolving more and more of the turbulent kinetic energy that is actually present in this configuration. The important part is now, before we go back to the equations, is that we can see that this frequency corresponds to the kind of cutoff, right? At some point, we don't get any further. You can see that, for example, for the green or for the blue curve, they start to fade off into a very deep slope, somewhere around 1 kilohertz. While for the red or the orange ones, they only start to fade off at maybe 500 kilohertz.
Yep.
And 5 kilohertz, I'm sorry. Around 5 kilohertz. And that means we are just resolving more and more of that spectrum.
And the important thing here as well, this pretty much tells us everything that we need to know about the LES idea, which is as you increase the number of cells, the mesh gets finer, so you start to pick up more of the energy in the small scale stuff, which is what we're seeing here with the higher frequency, generally speaking. Is that correct?
Yes, exactly. That is exactly the point. And this is where the additional temporal filtering that HTLES brings now actually comes in. So if we go back to those equations, keep in mind that the omega you're seeing here, basically omega just converted with a 2 pi, can be represented as the frequency f we just saw in the diagram. So just keep in mind whenever you see the omega here, you can think of it as the frequency, and there's just a common factor of 2 pi between those two. What we can see right here is a definition which says, well, the actual filter time width is 1 over that frequency. That kind of makes sense, right? 1 over the frequency means we have some filter width in seconds. Now the question is, what is this omega c? What is this cut-off frequency? And in classical LES or other hybrid RANS LES methods, this filter is either defined explicitly, right? This is something we talked about in the beginning. I'm really not an expert on that. Or it is defined implicitly via your mesh resolution, via your smallest cell sizes. And it's only dependent on the spatial scale. And in this case, the main achievement of HTLES is that the cutoff frequency is here defined, as I've said, it's actually quite easy to understand, as the minimum of either the spatial scales, which is the second part, delta x, right? or the temporal scales, which is the delta t. And it's actually quite a simple addition if you think about it. Instead of only filtering spatially, we can also filter temporally. And that gives us a very, very big advantage because it gives us the opportunity for every single cell. We can check are both the spatial and the temporal requirements reached to actually do the LES simulation. And if they are not, then locally the hybrid RANS model chooses its RANS approach.
Okay.
And if they are reached, so if my global time step and my local spatial step are small enough, then the model can choose to do LES locally. And this gives us a both dynamic and very adaptable approach to do hybrid RANS LES.
Yep. So could it be said then that the difference between DDES, which is the task eddy simulation for those listening who want to know more about it, and HTLES is that DDES has the temporal aspect more implicitly defined, whereas HTLES gives the user the explicit option to be able to change that independently, and that way you can fine-tune things how you like better.
No, it is still defined in an implicit manner. It is defined via the basically every cell locally checks
Okay,
my
sorry.
spatial and my temporal requirements achieved to do LES.
Yes. But you can set the temporal requirement explicitly, like in your own option, your own setting.
I think you could do that, but I think that is not the intended way. I think the major difference between something like when we talk about HTLES, it's that HTLES is part of a larger family called hybrid RANS LES models.
Yep.
And we have, you already said it, we have detached eddy simulation, we have delayed detached, improved delayed detached, we have zonal DES. There are many groups, many models inside of that family. And HTLS is one of those models inside of that family of hybrid RANS LES models.
Okay.
And the thing that makes it special, or what makes it especially usable for the application or for the actual CFD engineer, is that it is very dynamical in its approach. So you specifically do not have to predefine a lot of stuff.
Okay.
So when I do my actual simulation in StarCCM, for example, I simply run my normal RAN simulation, my normal URAN simulation, whatever I'm doing. Obviously, it has to be time dependent, right? I can't do it with a steady state simulation. But when I do a URAN simulation, I already have a global time step defined. I already have a mesh which has local cell sizes everywhere. And I can simply, by one checkbox, enable SRH, enable the HTLES model, which is called Scalable Resolvable Hybrid in StarCCM. I can simply enable HTLES, and then HTLES for me does the check whether any cell at all is even inside a possible LES simulation. And if it isn't, nothing changes. It stays a full RAN simulation.
Okay.
But if it detects, well, at this point in the mesh and this point in the region, there's actually a figure for this. If it detects, for example, right here, everything that is red is fully resolved by LES. Everything that is not red is going into the blue region, is not resolved by LES. So if it detects that your local cell size and your global time step size are small enough, it simply calculates the local region of cells with an LES approach. And if it doesn't detect that, it does it with a RANS approach. And that happens automatically and dynamically. And that means I actively don't have to do a lot of preparation to actually use it.
Okay. So in terms of the requirements for your mesh and your time step, what kind of things are you looking for? Because with the DES simulation, there's always to me, it's annoying where if you want to get a independent solution, not only cell-wise, the mesh-wise, but also time-step-wise, you have to like do a mesh independence test, then a time-step independence test, and ideally you need to go back and forth until they both converge and they don't differ anymore. And it's a very circular process that takes a lot of resources. Is there any difference with HTLES here?
Yes and no. Unfortunately, the key issue still remains, right? One of the important things to understand when we talk about large eddy simulations in general, whether it's being full wall resolved, wall modeled, or hybrid RANS LAS simulations, in all of those cases, we have the problem that at the smaller scales, when we do have the switch from actual resolved stuff, like actual resolved velocities from the large eddy simulation going into the subgrid scales, that means we go into some form of modeling for the last 20% of the turbulent kinetic energy. Whenever we do that, we change or we have an impact on the overall flow. And that means if I increase my resolution, for example, my spatial resolution, and I'm now resolving, let's say, 90% of the turbulent kinetic energy instead of 80, that might sound good in the beginning. That is obviously an improvement. But it also means that the last 10% now have a changed influence on the rest of the 90%. And that is a very difficult problem. You've already mentioned that exact thing, right? Where we have this kind of internal feedback loop, which means I can't simply do normal grid independent studies. So if you are already familiar with RANS CFD and how we use RANS CFD in practice, obviously we have to show that our solution is mesh or grid independent. We do that by simply scaling the mesh until infinity if possible, and hopefully see that with larger and larger mesh sizes, with higher and higher resolution, our solution stops to change. And if that is achieved, we can say, okay, at this point, for example, at 10 million or at 20 million cells, our mesh might be mesh independent, or solution is mesh independent. That is simply not possible for an LAS, because if I start increasing resolution, I'm changing the influence of the subgrid model. And that is a very, very difficult issue. So in practice, what do you do? Well, we are already looking at the two exact images which are important for us. And in figure 8, you see exactly the stuff we are used to from typical RANS simulations. We are simply scaling the cell count. And in this case, we are using two integrated quantities, the mass flow rate and the mean drag coefficient. And you can see they do somewhat scale, right? We do see the scaling, values change less and less. But this is unfortunately not enough, because we can't. This doesn't give us too much insight on the spectral stuff. So on the smaller scales,
temporal stuff,
which have less impact on the overall results. So if we look at that, we get back to the figure 9, which we already looked at, and this is what we see in figure 9. Here in this case, cell count is coupled to the time step. That means with higher cell count, time steps go the time step width goes down. And you can see we capture more and more of the turbulent kinetic energy, and that means our spectrum gets larger and larger, hopefully capturing more of the turbulent scales which actually matter to us. But you can see to actually get somewhat reasonably far, to actually get an improvement, we have to scale pretty aggressively. So we have to go on multiple orders of magnitude if necessary to actually get a reasonable scaling effect.
That brings me to our next question. In terms of resources, how does HTLES differ to DDES in terms of the time and computational resources required?
So in theory, it doesn't matter or doesn't differ that much. I think the biggest difference comes from how you are able to use it. So that is going back to what HTLES makes HTLES useful to me or to you as a CFD engineer. Because you can use it in a more dynamic way, because you can use it in a way where you might already have a URAN simulation and you might already be looking at time steps which might be on the order where LAS is possible, you can simply use those results to get your first insight. Once you do the full scaling, once you get into time steps and spatial resolutions, which are same or similar to DES, the actual computation shouldn't differ that much. The computational impact should be very similar. I think the big breakthrough or the actual improvement is in the workflow. Because my preparation, I don't have to do active preparation. I don't have to do, like, for example, in zonal DES, I have to, depending on the specific scheme, right? Don't get me wrong. I don't wanna step on anyone's toes. I'm not an expert in DES methods in general, but in many of the DES methods, we do have a lot of preparation time, and that preparation time and knowledge to set up a simulation correctly is something that pushes back, especially if you're talking about applied research and development or industrial applications, right? If you're an Airbus or Boeing, right, sure, you have your own compute clusters and you have an entire army of people working in your CFD labs. But if you're maybe in the medium scale industrial applications, there it's actually quite difficult to get away from RANs, right? We talked about that in the automotive the automotive scene, and I think the biggest hurdle is if you have to learn an entire new setup, an entirely new procedure, etc. You need specific setup steps. You need to know about perfect meshing, etc. That's a lot of hurdle to get over. But with HTLES, you can simply use your existing setup, enable a button, and it doesn't get worse. Because if it's just not good enough, HTLES will simply not touch it and just lets it be a normal RAN simulation with your underlying RAN's turbulence model, be it K omega SST, be it a Spallard-Almaraz. It simply lets that go, and it doesn't change anything. But if your simulation is both temporally and spatially resolved well enough, then it gets you hopefully an improved result. But
So
with all that in mind, I just want to stress very much that while it is an improvement and it is simpler than before, obviously it's the entire problem with CFD, as always, is it's easy to get colorful results. It's difficult to make sure they are correct. So that doesn't go away, right? This doesn't mean that like any company can just set your new applicant in front of a computer and let them run LAS simulations. That's not how it works. But it improves the workflow and it gives you more scalability from a lower level onwards. So you don't have to start out with a cluster. You can start out with your workstation. If it works, you can then scale it up. But especially in the setup, you can start quite low effort with your established RANs workflow.
Yeah. Okay. So this method that you have, that you're looking at now, HTLES, how did you come across it to begin with? Because you were telling me before where when you first started your PhD and earlier, you were looking at things in more general and you homed in on HTLES.
So in actuality, my PhD topic is not specifically on HTLES, and it still isn't. My research topic is more on focusing on improving the RANs workflows for specific operating conditions, right? In the beginning, we talked about the choked flow and the isentropic limit. And established RANS methods, they struggle especially around this isentropic limit. So as soon as we get the shock wave, we get something called a shock-induced boundary layer separation. Very complex phenomenon.
Yep.
And this is a kind of stuff where classical RANS turbulence models like your K omega SST, your realizable K epsilon, your Spallard-Almaraz model, they tend to struggle much more than in other regimes and other operating conditions. So my PhD work initially and still does focuses on these operating conditions and improving the RANS workflow inside of that operating conditions. That means, for practical terms, if you want to put it that way, I'm kind of trying to work out a optimized path of RANS settings. So, for example, take this model, but use a nonlinear constitutive relationship and then set this setting, and that should get you optimized results for these specific operating conditions. And that is kind of the overall thing. So improving RANS workflows with existing RANS turbulence models for shock-induced separation flows or for shockwave boundary layer interactions. Now, obviously, when you do a PhD and you try to propose some improvement, then very quickly your supervisor will come to you and ask you, well, I mean, that sounds very interesting, but how are you going to prove it?
Yeah.
And when you're doing CFD as a basis, you kind of have two things you can opt for. On one hand, you can opt for other higher order numerical methods, right? So if I do RANS stuff, I might be able to validate this relatively low order numerical method with a higher order numerical method, such as large eddy simulation. Or I can do experimental validation. We've already talked about that. That is difficult. We are doing that, but that is somewhat difficult to implement. So the way I came across HTLES is my trial or my way to get actually into scale resolving higher order numerical methods with the resources available to me.
Yeah.
Because I'm not working in a very big funded project. I'm unfortunately not studying somewhere with proximity to a large cluster or a large high performance computing cluster. So I have to deal with the resources I have.
Yeah.
And in this case, we are mostly talking about few node clusters, so maybe a few computational nodes. We are talking about your high performance workstation that's under your desk. So this kind of level of compute, but still able to get to reasonable scalable results. And this is where I stumbled over the HTLES approach, which enables, due to this dynamic scaling, enables you to start from the bottom, start from low requirements and gradually work up and see at what point do I get an improvement for my results without having to immediately jump for maybe a 100 node computational cluster.
Yeah. And honestly, that's probably the most important, or one of the most important things to improve, because like, even though you might go to places that have higher resources, for example, you could go somewhere that has 30,000 cores, but the thing is you might have 50 people trying to compete to use those cores, so you might only get 1,000 cores still. So being able to make things more accurate on regular computers is one of the most important things for actually development.
Absolutely. And that is exactly the hook I'm working with, right? Last time when I was at a conference and presenting our research, that was the exact hook I'm going for.
Yeah.
I'm an engineer. I'm not a physicist. I'm doing surprisingly fundamental research, but I'm still not I'm not doing fundamental research. And that means I'm always looking for the applied side. I'm always looking how this would go into an industrial application, how this would go in a publicly funded research lab, where we are not talking about infinite resources. We are talking about people trying to actually reach something, actually develop something. And at least for my part, obviously I can't speak about all other models. I want to stress that I'm not saying that other models aren't good as well, but just from my side, I've worked with HTLES.
Yep.
And the way it does enable me as an engineer to work with quite limited resources, but still be able to push into a region of scale resolving results, which I've not been able to do before, is something that just gives me new potential. And obviously that has to be validated, right? Just because it looks better, just because I'm seeing all these all these colorful pictures doesn't mean it's correct.
Yeah.
But if it is correct, then it gives me a completely new tool in my engineering tool belt as a CFD engineer.
Yeah. So on that topic, has this method of HTLES seen success in other fields that you know of?
Yes, it does have. It does have seen success. I think it has been validated mostly for incompressible flow cases. I think the authors of HTLES themselves, Dufal and et al., they have included validation cases in their own publications where they focus on showing and developing their model. The thing that I found very interesting is, which I only found out after I started working with the model, is that there has seemingly, to my knowledge, has not been any validation for compressible flows, or at least shock-dominated flows.
Okay.
So the exact application which I'm working with, so this choked flow where we have shock waves, shock-induced boundary layer separation, very complex interactions between shock waves and boundary layers. This is the exact case which HTLES has not been validated for. And if I may tell a quick story on the publication of this paper we're looking at, obviously whenever you publish a paper in a peer-reviewed journal, you get a peer review. And in that peer review, you get some other scientists, some other people in the field look at your work and ask you some critical questions and give you some feedback on your work. And one of the reviewers pushed very heavily into that direction. Well, what do we know about the validation actually?
Yeah.
And that is kind of the reason, the direction I'm working on right now, because that is a very, very valid point, right? These results, they look good. They look reasonable. They make sense. So they pass a plausibility check, and they fit into the other results we've collected so far. But that doesn't mean that the improvements which they promise, so we can talk about that later a little bit if you want, the improvements that they promise overruns are actually correct. And that is something that we are working on right now to actually show, okay, if we check that, if we cross-validate this with experimental data, we do see that the improvements are real and that HTLES can be used for this application.
Okay. So speaking of such, what simulations have you done so far, not just with HTLES on Hyperloops or anything?
Overall, in my entire career, that's a lot of simulations. So the main focus in my research or for my PhD is two things at the same time. On one hand, I want to capture a large parameter space, right? We've talked about Mach number as an input parameter. We've talked about the blockage ratio as an input parameter. We might have other input parameters, for example, the actual vacuum inside the tube. We are always talking about a vacuum, but as you know, there is no actual vacuum. We are just reducing the pressure. So
dramatically,
we might have 0.1 bars of pressure in the tube. We might have 0.01 bars of pressure. There is a lot of scalability in that, and that means we are spanning a very wide parameter space, and that is one part of my PhD research that I want to cover a relatively large part of that parameter space and show that the improvements I'm proposing for the RANS methods actually work over that parameter space.
Okay.
On the other hand, and this is where this paper, which we're looking at right now, comes in, for some specific cases, especially near that isentropic limit, where we get that change from relatively low drag to extremely increased drag,
Yeah.
where the current RANS models struggle so much in exactly this configuration, I'm also interested in showing what kind of improvements can we get specific to that regime, specific to that operating condition. And one of the things, you've already looked at this paper before at your channel, and you've focused very much on the mean results.
Yep.
And you very rightly pointed out that looking at the results, I mean, why even do this, right? Why are we even putting in that effort if the results, for example, comparing here between the HTLES and the URANS results, why do we even put in that much effort if it doesn't get us that much further? And one of the key things that this paper focuses on is the spectral results.
Yep.
And if we have a look at this diagram, let's focus on diagram A and B here. If we look at these diagrams, we can see two important things. First of all, we do have a lot of spectral content in this, right? This is a Fourier transform of the drag coefficient. That means we are seeing how much does the drag of the pod change over time, and especially what kind of influence each frequency has. Why is that important? Well, for example, if you think about sitting on a bus or driving with a train, and maybe you know this, you're tired, you're leaning your head against the window of the bus.
It's vibrating.
And when you are living in a city like I am, then this is a very headache-inducing situation, right? You wanna relax your head, but in actuality, you're getting these frequencies are so annoying. They are actually exciting your body, and so these frequencies are very important. So the type of frequency that can both excite the structure of the pod. This is something that's obviously important to safety, and they might lead to passenger discomfort. So it's important to get an overview of the spectral content. That means what kind of influence each frequency has. And this is what figure A shows, right? We do see that lower frequencies have a higher impact. That's what we expect. And we also see that if we compare different Mach numbers without looking at a individual line, we do see there is some difference. If we now look at figure B, we have the same results as before, right? These curves here above are the same as in figure A.
Yep.
And we also have the results from the URAN simulation.
Yeah.
And what you can see is there is orders of magnitude between the actual impact that a frequency has on the flow between the URANs and the HTLES. So that tells us that the URAN simulation is simply not able to recover these spectral insights, which might be very important in early development phases to both the overall safety and passenger comfort or discomfort during a ride.
Yep. And a couple of things extra that this also shows. So this could be used for things like noise production. If you have a better spectral frequency resolution, that is going to give you more accurate noise results as well from your CFD.
Yeah, absolutely. In this case, right, it's a CFD of a integrated quantity, so it wouldn't directly reflect the noise, but this exact diagram could be produced, for example, of a virtual sound probe within the flow, and you could be able, from an LES simulation, you would be able to reproduce it directly. From a URAN simulation, you can do that as well, but you then have additional models that translate that into a broadband noise spectrum.
Yeah, but being able to resolve and predict the drag and pressure fluctuations effectively means that you can also see what the stresses on different components will be from a structural point of view. So there are additional applications, not just the drag coefficient, but there are other things that would benefit from having a more accurate frequency spectrum too.
Exactly. In this case, the drag coefficient basically is one representative value, but you've rightly pointed out that this gives us a lot of insight on individual components if we wanted to focus on that. For example, if a company wanted to do development on that. And one thing I want to stress here, which is something I have seen in some discussions, is that people are always confused by this take. They say, well, obviously URANS does not produce the same spectral results. That's obvious. What is your insight here? And that is a very, very important thing to keep in mind, because that is generally correct. URANS is much more dampened or is much more dampening than an LES approach. That means we would never expect URANS to fully capture or match the spectral results. I'm 100% with that. The thing that is so interesting about this is the following. This kind of behavior we are seeing here is called, or is very similar to something called transonic shock buffet. Buffet is simply the movement of the shockwave moving fore and aft, etc. So when the shockwave moves, that movement might do some excitation, and in this case, we see that movement of the shockwave reflected in the drag coefficient. Very interestingly, a very similar physical effect, this transonic shock buffet, if we look at it from an wing aerodynamic side, is actually captured by many URANS models. So when we look at transonic shock buffet on a slender body, right? We've begun this entire topic by talking about blunt and bluff bodies, right? This paper is on blunt bodies. But if we look at a similar effect on a slender body, like a wing on an aircraft, then years of research show us that URANS can actually resolve these frequency. URANS has been shown multiple times for more than 20 years that it does or can capture, under specific circumstances, not always, but it can capture the spectral component of a shock buffet, so of a shock movement on a wing. Now, in our blunt body, it looks very similar. It seems to be very similar. We have a shock-induced separation. We have this kind of separation cycle. We can have a look at the separation cycle as a small video clip if you want. We have this separation cycle, and it looks very similar to transonic shock buffet on a wing, which is resolvable by URANS, but in our case, we show that it is not resolved by URANS. And that is the interesting result here. URANS kind of should be working, but it doesn't. And HTLES does. And that is the main takeaway from this.
And also another thing would be how much it doesn't. So it's not just about that it doesn't, but how far off is it? Because if it's within a few percent, sometimes that could be good enough. If it's with 10%, that's other times it'll be good enough, other times it won't. So it's also interesting to know how much off it is.
And we have seen for the mean drag, it is quite all right. There's no need to do HTLES to predict the mean drag coefficient. That is simply not necessary. It still might be interesting to predict like a range, what min and max values do we have, but for an actual temporally mean value, it is not necessary. But as soon as we get into any spectral data, which might be interesting for some applications, might not be interesting for other applications, but if you need it, then URANS simply outright fails to predict that in a reasonable manner.
So you mentioned some videos, and you showed me a few videos, and I was quite fortunate to see them. So this is one video from your CFD?
Yes, exactly. So what you're seeing right here, let me do a quick introduction. In the paper, we have at the very end, we have these two images. And just before we look at the video, let's actually understand what we are seeing. Let's take the B image, which is more interesting. We see two things at the same time. First of all, we see at the background is a numerical Schlieren image. A Schlieren image is a representation of the density gradient within the fluid field. That means when you see something going very, very dark, as here, it simply means there is a very large gradient. And obviously a large gradient would be associated with a shock wave. So in this case, you can see a very, very dark means shock wave. Light dark often means something like a Mach wave, which is a density disturbance, but it's not as strong as a shock wave. And back here, you might even see something which may be sound waves practically. And all of these are captured by the background, which is a Schlieren representation. In the foreground, you are seeing a basically an isosurface with a constant Q criterion that, for all intents and purposes, it simply means it shows us a certain level of vorticity or turbulence in the field. So it tries to capture the different scales. You can see right here, for example, down at the bottom where my mouse cursor is, you can see quite small structures. At the top, you can see quite large structures. And a Q criterion isosurface means we can capture these different scales. And this Q criterion is then colored by the Mach number.
So just a quick note on this, if you were to use like RANDs, these Q criteria isosurfaces would be far fewer and or far less detailed. The going to DDES, HTLES, and LES results in more of these details coming out.
Exactly. And you can see that quite well if you actually look at the moving image, right? Maybe you can start looking at this point right here.
Yep.
So at the foot of the shock wave, we can see two things. First of all, that the shock is moving, right? We do see that the foot is actually slightly moving forward, then it's moving backward, and it's moving forward again. So we can see this kind of movement, this kind of transonic shock buffet. But we can also see the immense turbulence production happening at this foot of the shock wave. And this is exactly why we call it a shock-induced boundary layer separation. So we have this separation, and the separation leads to turbulence production. And in this case, it is induced by the shock wave itself. The other interesting thing you can see, if you just follow along with the flow, you can see that these waves are actually traveling upstream, right? You can follow them and you can see them traveling upstream. In this case, if we had a case for a slightly lower Mach number, it would be even more visible. I think this was a great example. If you follow along this wave, you can see it and then collapsing into the shock wave. That is very interesting to see because the reason for transonic shock buffet, or the actual physics mechanisms behind transonic shock buffet, are not yet fully understood. And the most agreed on consensus is that this shock-induced separation and the resulting buffet, so the resulting shock motion, is likely due to a coupling between the separated regions and the shock wave via sound waves.
Okay.
So
an acoustic feedback.
An acoustic feedback loop, and maybe, I'm truly not saying that this is conclusive or anything, 100% not, but it is interesting to see it. And we are not at scales where we would expect to resolve all temporal scales or spatial scales, but it is interesting to see that at least some sort of Mach wave or sound wave similar structure is moving upstream, and that it does interact with the shock itself.
And one thing I want to point out to the viewer is that this is actually not very close to typical transonic speeds. So transonic speeds, if you were to talk about a plane, it would be like Mach 0.8, Mach 0.9. Because this is a bluff body and the blockage ratio is so high, the transonic speed here is actually much lower.
Exactly. So for the incoming air, right here we are only seeing the rear of the pod. The incoming air, which is coming, imagine from the very left side, a few meters in front of the part we are seeing, that air might only be entering at 150 meters per second, so something like Mach 0.5. In this case, we are looking at specific boundary conditions, blockage ratio 0.2, and a Mach number of 0.6. As you correctly pointed out, for an airplane, a Mach number of 0.6 would be well below any transonic effects. But because we have this blockage ratio, which means we have a high local acceleration, because we have this pinching effect of the outer walls, the flow has to get faster and faster. We do get to a point where the local Mach number just in front of the shock is well above 1. And this is where we do then actually get a shock wave.
Okay, so I was also fortunate enough to see some of your experimental results that corroborate and even validate your CFD to some extent. Would you be interested to share those here?
Yes, absolutely. So just as a small introduction, so we have talked in the very beginning, we've talked about that experimental results are very difficult to obtain with this kind of setup, right? You either have to build an entire Hyperloop tube network, which is possible. Again, there is some work towards that, even for compressible flow cases, I believe in South Korea. Or you have to do it with a wind tunnel setup where you would need a moving wall boundary. Either of those cases are not obtainable for me, unfortunately. But we have used a common approach in CFD validation, and that is kind of building a logical thread to follow along. So what does it mean? Well, in our case, we are not simulating the actual conditions. We are not having a moving wall boundary. We cannot build a wind tunnel like that. But what we can do is we can create a proxy case, basically, that kind of has similar flow features, which might also have the shock-induced boundary layer separation, which might also have the transonic shock buffet, so which has the important physical mechanisms which we need to validate, but which does not perfectly reflect an actual Hyperloop setup. And that is exactly what we did for this case. So let me show you the following video. So before I let that run, let me give you a little bit of insight what you're seeing right here. So first of all, you might be able to spot right at the back where my mouse is right now, you can see that we have this kind of similar shape, this kind of similar fall of the pod. That is the whole idea of this setup, right? We are not modeling an entire pod or entire capsule. We are simply modeling a part of the rear in the hope to somewhat reproduce the same physical mechanisms. And in this case, you are seeing a black and white pseudo-Schlieren image. So it's similar to the Schlieren image we just saw in the numerical video. In this case, it is produced by a different setup. It is produced by an infinite fringe differential interferometry. I only understood our setup a few weeks ago myself. But in practice, what matters to us is that it produces a Schlieren-like image. So it's very similar in the sense that a dark color, like here, marks a shock wave, and that this is a measure for our gradient. Interestingly, you can also see the boundary layer right here, right? The boundary layer also has a velocity and thereby density gradient. And you can see back here the actual flow separation, which is marked by very slow air at some stage, but also just a so-called entropy line, which means that we have a difference in thermodynamical quantities. And if we now have a look at this video, this is captured at, I believe, 10,000 FPS. That means we are capturing at 10 kilohertz. You can see two things. First of all, we do have a at least similar looking overall shock structure, right? We do have we do have a shock wave. We have a separation at the foot of the shock wave, but you can also see that we are not perfectly matching the boundary conditions. So obviously at the top, for example, we do have a clear difference because our wall at the top is not moving. Okay. But this was our key focus. Now, obviously, the important thing is to match the actual conditions that are interesting. And this is why I brought up this idea of a proxy case. And what we did is we actually created a kind of digital model of our wind tunnel, including the entire geometric setup you're seeing right now, and including the inlet section, the outlet section, etc. Like our entire wind tunnel is modeled in CAD. And with this CAD model, we were able to then kind of validate whether the HTLES model was able to predict the exact same physics for this case. And if we have a look at this image, this video, for example, very similar setup, you can see we have a different configuration, which we were able to reach with different boundary conditions, and we do get a different behavior. And this is exactly the kind of proxy setups we are then able to take, run with our HTLES setup, where we match the exact geometry. That means we are not validating HTLES for hyperloops. We are validating HTLES for physical working mechanisms which occur in Hyperloop applications. And that is kind of the logical thread to follow, where we can't validate the thing directly, but we can validate a step in between as a proxy in between the two things, and then by logically following that, we kind of have this validation chain, basically.
Yeah, that's actually not that different to a lot of CFD methods. Like a lot of the time, you won't ever validate your CFD for every single experimental case that you run. You just validate it for one particular case that you say is representative of what you're looking at, and then use your CFD from there. So that's actually quite common to see. Exactly.
And we hope that this gives us at least enough confidence to say, well, if we can match those results, which our preliminary analysis shows that we can match them, especially the spectral component, if we can match those quite well between the wind tunnel and the proxy CFD model, then we can then infer from that HTLES is actually usable as a higher order method to validate RANS results. And that gives us this very useful chain of validation.
Yep. So with your validation so far, what has been the results?
So for now, we have focused on trying to capture the exact geometry of the wind tunnel and then reproduce that. I can show you some results, but I want to stress that these are very preliminary and have not undergone the same post-processing that you would see in the previous videos we've looked at. So before we actually look at these results, I want to give you a little bit of context again. So I already said this is not of the usual level of post-processing. This is very preliminary. Difficult word. This is very preliminary results, but they are just for us to do a kind of proof of concept that it does work, and we might follow up on this. So What you're seeing right here is actually sampled at a higher frequency. I believe this is at 100 kilohertz because we need that resolution to actually, for LES to actually kick in. That also means you're looking at a much slower movement, but obviously that is just a this is just an offset because one is sampled at 10 kilohertz, the other one is sampled at 100 kilohertz. It still represents the same motion. But what you can see is that we are able to match this kind of behavior that we just saw in the second wind tunnel video, where we didn't have this one standing shockwave which slightly moved, but we had this always moving upstream shockwave, then getting too weak, and then a new shockwave forming and moving upstream again. And this kind of cycle is always repeating, and we do have very similar results from the wind tunnel and the CFD results, and that was very exciting for us to see, to actually get the results. We've also done some preliminary results with URANs only, and obviously when you do a URANs you would not be able to resolve this kind of results where you have these practically these eddies being represented in the Schlieren image. That would not be able, but what we are focusing on is, can it resolve the spectral results of the shock movement itself, of the shock oscillation. And so far we believe that URANs again is not able to do that. But it obviously also depends on operating conditions and on exact setup. So that is something I can't really give you a definitive result on, because we don't have it yet. But it seems like on one hand, HTLES can be somewhat is validatable by this, and on the other hand, URANs is again not being able to capture the spectral results, which might be interesting for the engineers developing this kind of technology.
Yeah. So pretty much from this we can conclude with this HTLES that it's getting the big scale stuff, large scale stuff correct, at the very least with this movement plus the frequency aspects.
Yes, that would be my preliminary conclusion, yes.
Yeah. And then the one thing I was interested in was that, so the Hyperloops travel at different speeds. As we saw, you had two different CFD pictures, one of 0.57 and 0.625. How does this validation at one speed translate to another speed?
So one of the practical challenges for us when we wanted to do the validation in the wind tunnel was to obviously get this setup tuned correctly, because in our real world example, we would actually have the airflow at an exact Mach number come in, interact with the pod, and go out. In our case, we don't have a pod per se. We kind of use the entire wind tunnel with some specific geometric changes as the pod itself. And that gave us the challenge that we could not simply use a inlet Mach number as we would do in a CFD. We kind of have to deal with the Mach number that starts to appear. This sounds a little bit weird, but in supersonic or transonic wind tunnels, the air kind of decides on itself what it wants to do. You can only give it some outer boundary conditions, and then it chooses its own path, obviously based on the laws of physics. But it's more difficult to directly influence the flow. And with our wind tunnel setup, what we had to do is we used the supersonic diffuser, which is downstream of the section you're looking at right now. And this diffuser gave us the option to change the cross-section behind this part, and this produces a certain back pressure. So a back pressure acting onto the flow in the actual main section we are interested in. And with this back pressure, we are able to produce different operating conditions as if we were changing the actual inflow Mach number in front of the pod.
So given that this is where the field is currently, what do you think is needed for the future, the next steps immediately for this research, and then from then on?
I think that really depends on the kind of angle you take on the research we've talked about today. On one hand, I think from a more fundamental approach, from a more generalistic view, the research on more turbulence models, on HTLES as a method, etc., is a very ongoing application and use case. So that means that I think it's not very simple to say we need this step. I think the application of HTLES for this kind of application and for compressible flows, for flows with shock waves, be it for a rocket, be it for a supersonic airliner, whatever you want to have, I think this is a very continuous spectrum where you can, where the current state of research is very comparable and very similar to what we saw a few years ago with general hybrid trans-LAS methods. So it's always moving forward. In the sense for the Hyperloop specifically, I think much of the research has to now transform into more applied and more engineering applications. I think we have seen a lot of CFD work on in that field. There are a lot of very interesting papers that came before this one, and it's quite a recent research field, which makes it very exciting. But it also means that at some point it has to somewhat grow and get into the next part. And for example, in this paper or in this podcast today, we only focused on very specific subcases. In general, a lot of the CFD research on Hyperloops is focused on focusing on the transient effects, on the kind of piston effect you get in front of the pod, all this stuff which we already have simplified away to look at more fundamental things. But now is the time that these fundamental things kind of move upward into the chain of more applied stuff, applied research, and hopefully at some point into some actual industrial research and development, be it of some Hyperloop directly or some other application which focuses and is built upon similar physical working mechanisms.
Okay. And one final question that I have, at the start of the podcast episode, you mentioned how Hyperloops are they're not a new thing. They've been around for quite a while, and they're actually called different names throughout the years. Can you give us a bit of a history about that if you know?
Unfortunately, I forgot the name of the original inventor, let's call him, but I think it was in 1799, so a very long time ago, when someone came up with the idea of a VAC train, so vacuum train. And I think it is a somewhat obvious idea to have, not saying that it wasn't a good idea to have, but saying that I think people would at some point levitate towards that. If you think about where does drag come from, drag obviously comes from interaction with the air. So if we take away that air, we reduce drag. So,
no drag.
I think that that idea is very old, and again was already coined. The term vectran was already coined more than 200 years ago. The actual development, obviously, of the new stuff, which we call Hyperloop now, is a lot newer. But if you're interested in that, I think it might be surprising to learn that a lot of the research is actually from before, when I think SpaceX opened that university challenge actually for university teams to compete, that there was actually a lot of research on the overall topic before that. And you also have to keep in mind that a lot of the physics which are relevant in our case, for example, the blockage ratio, impact, etc., they are also relevant for current train systems. If a conventional high-speed train enters a tunnel, you can feel that in your ears, right? You can feel that in your ears because that is a pressure wave. And a pressure wave, which gets stronger and stronger and stronger, ends in a shock wave. So if we talk about conventional high-speed trains, there is even some overlap with that. So I think that research is very well interconnected with that, and the history is much broader and more interesting than only the 2013 SpaceX white paper, which coined the term Hyperloop. There's a much more behind that from before that era.
Okay, thank you. That brings us to the end of this podcast episode. I really liked it, especially your validation videos and your numerical videos as well. They had a lot of details in there. And thank you to Benedikt for coming on and being a mad lad with us. If anyone is watching this and wants to get in touch with you, how could they do that?
I think most easily is if you Google my name, you will find my publications. You can get in touch with me via LinkedIn. I think if you want, you can link that below in the YouTube description if people wanna have a look. So if you want to have a discussion or talk with me, I'm very happy to answer your questions via LinkedIn. And otherwise, you can always find my research on Google Scholar and Research Hub and follow my progress there.
Yeah. And anything else you wanted to mention, or we've covered everything?
I think we've
covered a lot.
Talked enough for the people that followed along. So if you have reached this point, thank you very much for staying on. Thank you for having me. It was very interesting to discuss that. It's not very often that you can actually discuss your research topic in such a depth, while at the same time talking to someone who can translate that and steer that direction for a broader audience, right? We are all, I'm just usually talking to colleagues in the field, which are also scientists, also engineers, which might know the same stuff as I do, but talking with you, that gave me a good opportunity to reflect on that, and hopefully your viewers actually got some interesting stuff to take away.
I'm sure they did. I definitely did. I learned some things in this time, and before we were talking on this video, before this video we recorded, we were talking about some things that I wanted you to explain it during the video because I thought it was so good. I think everyone else had the same kind of feeling. And talking with me, I hope, has been better than just talking to yourself. And I'm guessing that talking with your colleagues is also rewarding because you find other ideas from them. But yeah, we are very thankful to have you on here, Benedikt. We are grateful for that, and we have learned far more than I think you realize.
Thank you very much for having me.
Thank you. So if you like this episode, hit the me liking and subscribe buttons. And if you'd like to see an earlier podcast episode where I went through this paper of Benedikt's on how to simulate the Hyperloop with this method, check out this video here. Peace out, amigos.